Okay? So the one we talked about yesterday was dipole-dipole attraction. So the next slide, I'm just going to go to the next slide here in a second. We're going to talk about hydrogen bonding. So if you want to write hydrogen bonding down there, you can. This here I put 4. So it's bonded to 4 elements. So hydrogen bonding happens when you got a hydrogen present, and it's bonded to one of those 4 elements. Okay. If you notice something about these 4 elements, they're all the highest 4 electronegativities. Fluorine's 4, oxygen's 3.4, nitrogen's 3, and chlorine's around 3. So they're all pretty high electronegativities in relationship to hydrogen. Hydrogen's 2.2. So hydrogen's kind of the lowest when you make those pairings. So the difference between hydrogen and these elements in electronegativity is quite large. So that creates a situation where hydrogen's highly polar positive. And because it's highly polar positive, then we'll show examples of that here on this next slide. Okay. So don't write right away, okay? Because I need to explain it. So don't write right away. So over here, this is hydrogen and oxygen, and I just need to explain something real quick with that. Before you write it down, okay, based upon what we talked about yesterday. So hydrogen is 2.2, and oxygen is higher on your list. It is 3.5, so that's 2.1 and 3.5, which is a 1.4 difference. And that's pretty high for polarity. So that's why we have, remember when we did this, we had the arrows. We had the arrows pointing toward the oxygen. You guys remember that from yesterday? Why is it pointing toward oxygen? There you go. So it's a higher electronegativity. And because it's a higher electronegativity, it's going to be negative because the sharing is way closer to oxygen than hydrogen. Okay, now this little dotted line here represents kind of a weaker bond. Remember, we do a solid line is covalent. So the dotted line is going to represent kind of a force that there's attraction between these 2 areas. Because this area of the water molecule is negative, and then the area of the hydrogen is positive. So there's a little bit of a dotted line that kind of connects those 2. Okay, if you want to show it. Any questions with that? Any thoughts? Any concerns with you on that drawing that you don't understand? Okay, now we go over to hydrogen bonding. So I want you to look at hydrogen bonding and kind of what's the difference? Because really it looks like it's the same situation, but what's the difference between the 2, do you think?
There's 3.
What's that?
There's 3 of them instead of 2.
Right. Okay, there's 2, but let's just focus on, 2 of them where we see the dotted lines.
It goes down to one of the pairs.
Yes. So, what do we know about these pair of electrons here? What charge are they? Electrons are negative. Okay? So, and in hydrogen, we said this whole region, but hydrogen itself. Now, this is a region, right? This region is positive. You guys agree with that? But hydrogen individually is also positive, right? So because of that, there's an attraction between that hydrogen and an unshared pair of electrons. So if another molecule doesn't have some unshared pair of electrons, do you think there'll be an attraction between the... No, there won't be. Right? So if we have another molecule floating around that's polar, but there's no lone pairs of electrons for some reason, there won't be an attraction there. But you guys see the difference? This is not a region. This is like this hydrogen right here is being attracted to that unshared pair of electrons. Same here, this hydrogen is being attracted. So water has two things going on when we look at intermolecular forces, right? It has dipole-dipole forces because the region of the hydrogen region is positive and the oxygen region is negative. And it also have hydrogen bonding where you have H that's attracted to the unshared pair of electrons on the oxygen. So there's an attraction there. If you notice, these two attractions deal with electrostatic forces, which are negative and positive values. Okay, that's something slightly negative, slightly positive. Any questions on hydrogen bonding? So anytime you have, okay, an H bonded to one of those four, and you have another molecule with some unshared and lone pairs showing, then you're going to have hydrogen bonding of some sort. Got it? Usually this is the strongest of the four, or strongest of the three. So if something has hydrogen bonding, that's usually the strongest. Dipole-dipole attraction is usually next, depending upon the difference in the polarity. And then the last one is quite unique. Okay, it's called dispersion forces. If you look at the bottom of page 299, they talk about this thing called a very weak attraction called dispersion forces. Okay, so I'm not going to explain how that happens, but what I'm going to tell you is results where we will have higher dispersion forces. Okay? So if you look at the drawing on page 299, what happens is these electrons are moving around the atom, and for some reason, sometimes they get kind of isolated on one side of the atom. So on that one side of the atom, it would be negative, and on the other side, it's slightly positive. But this is the weakest of the four. So if we had to list them in order, hydrogen bonding is number one in attraction. Dipole-dipole forces are number two, if there's a pretty good difference in their electronegativity. And number three is London dispersion forces. So what do you look for in a particular atom or molecule that will tell you that it probably has larger forces? So, if the molecule has a greater number of electrons, okay? So I'll list a couple out, and you tell me which one you think will have greater attraction. So I'm just going to put up here greater dispersion force. Which one? Okay, so I'm going to go argon or neon. So on that number one. So which one has a greater force, argon or neon, based upon dispersion forces? So look on your periodic table and tell me which one you think.
Argon.
Argon, why?
Has 18 electrons if it's 0 and minus 10.
Yes. So argon has a greater London dispersion force. Let me kind of get that. 18 electrons for argon. So argon would be greater. Questions on that one? Okay. All right, let's do another one. Let's do a molecule here. Let's go CO2 or H2O. So which one has a greater mass, H2O or CO2? CO2. You guys know how to find molar mass, right? Oxygen, you got two of them, that'd be 32 plus 12 is 44. And then water is 2 plus 16 is 18. So this has a greater, now, it doesn't have a greater overall intermolecular force. Water is going to have a greater intermolecular force than CO2 for a variety of reasons, and we can talk about that later. But if we're just looking at number 3, and that's it. Does everybody agree with that? Okay, larger atoms. I'm going to go ahead and give you a couple to choose from. Let's go with let's go nitrogen or fluorine. What do you think? So look at the periodic table. Which of those two is larger, nitrogen or fluorine? Remember our trend going across? What happens to the size of the atom as you go from left to right? It gets smaller, right? So which one would be bigger? Nitrogen, right? So you got to use that trend. You guys know that trend on size of atom. If you go left to right, they get smaller. That's the trend. So then longer chains. That should be chains with a I behind that. Okay? So longer chains. So I'm going to give you, what I mean by chain, I'm going to give you a little chain. Because a lot of times we have multiple atoms hooked together. So let's give you a chain. I'm going to switch the slide here real quick so that I can draw a chain. Which one of those two is going to have greater London dispersion force? Bottom one, right? Questions you guys have. So, now, when we're looking at this, we're just looking at London dispersion force. We're not looking at all those other. So, to decide if something has larger overall intermolecular forces, you got to look at 3 things. You got to look at hydrogen bonding, dipole-dipole, meaning that it's going to be a polar molecule, and then this is the last thing you look at. And then from the combination of all 3, you determine if something has larger or lesser intermolecular forces in total. So if it has what, when you look at it, and the other substance doesn't have it, you would probably say it would have higher intermolecular forces. So what would you look at first if you had to differentiate between the two? Hydrogen bonding would be number 1. If it has hydrogen bonding, guess what? It will be bigger. Okay, if the other one doesn't. Next thing you look is if it's polar. So if one's polar and the other one is not polar or doesn't have hydrogen bonding, that's your second thing you look at. And the last thing you look at, if neither one of them are present, we don't have hydrogen bonding or polar molecule, dipole-dipole, then you have to look at these 4 characteristics. Does that make sense? Okay. All right, good. Here in a second, I'm going to give you guys